Hi everyone, welcome back. In this lecture we're going to continue counting techniques. In this case we're going to focus though just on counting objects in graphs. So the idea is we've introduced a number of combinatorial objects right at the start of this course. We've introduced what graphs are. Now we're going to look at counting within graphs. We're going to introduce a few more ideas surrounding graphs, basically some kind of structure on graphs. But the goal is to just come up with more combinatorial objects that we can get counting with. Our goal is to count things and to explore counting techniques. So I wouldn't consider this a formal introduction to graph theory at this point. That'll come in the second part of the course. Later on in the course we'll actually dive really into graph theory. Right now I'm just introducing enough graph theory so that we have objects to count with. So let's dive in. So in this example we want to draw the graph G, which has vertex set 1 through 5 and the edge set as listed. So let's draw it out. So we got vertex 1, vertex 2, 3, 4, and 5. Our edges go from 1 to 3, 1 to 4, 2 to 4, and 2 to 5. Now, upon looking at this, you may say, oh, that's just a path. So why didn't I just draw it as a straight path? Why did I lay it out in this sort of weird way? Well, the idea is, from this diagram, I can see that our vertices really come in two types, two sets. I'll call this first set V1 and this second set V2. So these are capital V's. Maybe I'll try to distinguish them by putting little hats on them. So these are capital V's, so these are two sets of vertices. So I've taken my vertex set V, I've split it up into these two subsets. And what do we notice about these? Well, there's no edge in this graph, no edge between vertices in V1 and no edge between vertices in V2. In other words, there's no edge that connects a vertex in V1 with another vertex in V1, or a vertex in V2 with another vertex in V2. All the edges seem to go across. They go from one vertex in one of the sets to a vertex in another set. This is known as a bipartite graph. So our definition is below. What is a bipartite graph? It is a graph where we can partition the vertices into two non-empty sets which satisfy the following. The conditions are that V1 intersect V2 is empty, so these are disjoint sets, and they unite to all of V. That's really what we mean by a partition. So that's just a description of what a partition is. It's splitting up the set into two non-empty subsets which are disjoint and unite to the whole set. The last property says that every edge in E is incident with one vertex in V1 and one vertex in V2. So in other words, our edges sort of bridge across these two sets. That's what a bipartite graph is. So as a follow-up definition, we can describe what we mean by the complete bipartite graph, K, N sub M. So here we've used capital K. In the past we've used it to denote the complete graph. So K sub N is the complete graph on N vertices. So it's the graph with N vertices where every edge that's possible is in the graph. Here we're going to borrow that notation, capital K again, but we're going to use two subscripts, N comma M. And what this is it's the complete bipartite graph. So this is, we've got one collection of vertices of size n, another collection of vertices of size m. Those are the two halves of the bipartition. And the edges just go from one of those vertex sets to the other vertex set. So for example, if we want to draw our K23 graph, here's two vertices. Let's label them 1 and 2. And then we've got 3 vertices in the other half of the bipartition. We'll call those 3, 4, and 5. And the edges go from one of the vertices in one of the sets to a vertex in another set. Since this is a complete graph, all edges are possible. So we've got 1, 3, 1, 4, 1, 5. We don't include 1, 2 because vertex 1 and vertex 2 are in the same half of the bipartition. And similarly for 2, 2 would connect to all the vertices that are in the other set. And so there we go. We've got our K2, 3 drawn. And just for emphasis, I will group together those vertices. That's our V1 set, and this is our V2 set. Now we could follow up with the question, how many edges are in K2, 3? Of course, since we've drawn the graph, we can just go ahead and count them. But maybe there's another way we can think of counting the number of edges without actually physically going to the diagram and counting them off. Well, what would an edge look like? Well, an edge would look like it starts at a vertex and it goes to another vertex. And so I'm drawing these as boxes as if they are slots which we will fill. So this vertex slot would be filled with a vertex from V1. So this would contain a vertex from the set V1, and this slot gets filled with a vertex from V2. How many choices are there? For that first slot, how many choices? So if it's a vertex from V1, there are 2 choices to fill that slot. And this one is going to be filled with a vertex from V2. There are 3 choices for that slot. So there are going to be 2 times 3 ways to fill those 2 slots. Now I have to think, did I overcount? Did I count the same edge twice? 2 different ways? No, because I'm just looking at this as an edge. It's got a vertex coming from V1, so I'll just make that the left vertex, and it's got a vertex coming from V2, which I've put on the right. And so it's got 2 times 3, or 6 ways to choose vertices to fill these slots. And so what that means is, therefore, there are 6 edges in K2, 3. So this is an example of the kind of counting we are going to be doing in this section. Let's have a look at the next collection of problems. How many edges are in a path on n vertices? So we've got a path on n vertices. How many edges are there? So you might know this immediately off the top of your head. It would be good if we get to that stage. A lot of these basic questions that I'm going to be running through in this lecture are questions that we're going to count once, and then they're things that we should know because we're going to build off of them in future classes. So how many edges are there in a path on n vertices? There are n minus 1 edges. Why is that? Well, a path on n vertices looks like this. It starts at a vertex, then it's got an edge to another vertex, an edge to another vertex, and so on, all the way to, in this case, vertex n. And so what is our edge count? Well, we have a first edge, a second edge, a third edge, and if you notice, the subscript that I'm writing on the edge is just matching the vertex label on its left end. So that means when I get all the way down here, this is an e sub n minus 1, and so that means there are n minus 1 edges. How about 2? How many edges are in a cycle on n vertices? Well, you may know the answer to this immediately as well. There are going to be n edges. Why is that? Well, there's just one more than the path. So again, we can draw our cycle out. So we've got n minus 1 out to n, And then there's one more edge that connects the end vertex right back to the start. So if I label these, that's E1, E2, E3, En minus 1, and then the last edge is En, and so that means there are n edges. Well, the next question. How many edges are in Kn? How many edges are in Kn? So that's the complete graph on n vertices. How many edges are there? So there are n, choose 2 edges. So in these questions I'm going to write down the result, but I'll also justify it as well. As we go through these, pause the video, try to answer the questions yourself, and then verify with what we're doing. So how many edges are in Kn? There are n choose 2. Why is that? Well, an edge in Kn is determined by 2 vertices. So what that means is that the number of edges is equal to the number of ways to choose 2 vertices from n vertices, and that's n choose 2. How about the next one? How many edges are there in Kn sub m? So now that's the complete bipartite graph on vertex set n and another vertex set m. How many edges there are there in this case? You may think back to the example we did with K23, how many edges there were, and how we can do this in general. In this case, there are going to be n times m edges. Maybe I'll write the word edges by both of these to indicate that we are answering the question up here. Why is that? Well, an edge in Knm is given by an ordered pair of vertices. I can specify it by this pair v1, v2, where v1 is a vertex from the vertex set capital V1, and v2 is a vertex from the vertex set capital V2. So that means that the number of edges is equal to the number of ordered pairs. And how many ordered pairs are there? Well, there's n choices for V1 and m choices for V2. So it's the size of V1 times the size of V2, which is n times m. And so that's the number of edges we have in the complete bipartite graph Knm. How about the next example? How many graphs are there with n vertices? How many graphs are there with n vertices? So I've got a graph, it's got n vertices. I've laid out these n vertices. Now it's a question of choosing edges. So how many ways can I choose the edges to fill out this graph on n vertices? Well, for each edge in Kn, we can either use it or not. So we're either going to use it or not. So I'm thinking of the complete graph Kn, and I can either use a given edge or not use a given edge to make my graph. So that means there are 2 choices. So there are 2 choices for each edge. And so what that means is that the number of graphs is equal to the number of ways to select a subset from the edges in Kn. And how many edges are there in Kn? There are n choose 2 edges in Kn. That's what we worked out before. And so what this means is that for each of those n choose 2 edges, I can either use it or not. So we get a 2 to the n choose 2. That's the number of ways we can select a subset from the collection of all edges. So we'll write this answer in up here. This is 2 to the n choose 2. Now how about for the next one? 6. How many graphs have n vertices and m edges? So in this case, we've got a graph with n vertices, and I want to know how many ways can I fill m edges in. We can think of this again, taking the complete graph on n vertices and choosing m edges from the entire collection of edges. So this is the number of ways to choose m of n choose 2 edges, because that's how many edges there are in the complete graph. And how many ways are there to choose m of n choose 2 edges? Well, from our collection of n choose 2 edges, we want to choose m of them. And so that's how many graphs there are. So there are n choose 2 choose m. All right, how about the next question? Let v1 and v2 be two disjoint sets with the first vertex set being of size n1, the second vertex set being a set of size n2. How many graphs have bipartition v1, v2? So we'll get a little sketch of this. There's our vertex set v1. Here's our vertex set v2. This one has n2 vertices. This one has n1 vertices. For our vertices in here, they connect all the way across, and so on down the line. So we get all these edges going across. And what we want to do is we want to count how many graphs have bipartition v1, v2. So what I've drawn here is all the possible edges. So this is k, n1, n2. Now how many graphs have this bipartition? Well, each graph would be just determined by which edges it was using. Of all of the possible edges it had to choose from, we want to be able to select from those the edges that will make our graph. So in this case, this is question number 7. How many graphs are there? Well, the number of graphs is equal to the number of subsets of edges from k, n1, n2 we can choose. And so that's a collection of how many edges? Well, there's n1 times n2 edges. So that's my set of n1 times n2 possible edges, and I want to know how many subsets can I choose from that? Well, it'll be n1, n2, 2 to that power. How about number 8? How many graphs have bipartition v1, v2 and use exactly m edges? So I got the number of graphs with m edges. This would be the number of subsets of the edges in k, n1, n2 with size m. So how many size m subsets are there from this set here? Well, that is, there are n1 n2 possible edges to choose from, and I want to choose m of them. So it's n1, n2, choose m. So I'll fill in these values up here. We've got n1, n2, choose m. And the previous question 7, the answer was 2 to the n1, n2. So there we're counting objects in graphs right now, or in this case we're counting the number of types of graphs there are with a specific structure. And we're using our previous counting techniques. So let's have a look at the next one. So here's a definition. Definition is of a subgraph. So if G is a graph with vertex set V and edge set E, and G prime is another graph with vertex set V prime and edge set E prime, then G prime is a subgraph of G if its vertex set is a subset of the vertex set of G, and its edge set is a subset of the edge set of G. If the vertex set of G prime is V, then we call G prime a spanning subgraph of G. So let's have a look at an example. So we've got maybe this vertex set 1, 2, 3, 4, 5, and here's our edge set. I'll just draw a few edges in here. Something like this. So there's our graph G. And from this we can get a subgraph. So we'll say, what's a subgraph of G? Well, for example, it's got to have a subcollection of the original vertices. So maybe we'll take 2, 3, and 4. And then I also have to make sure that the edges that I'm using are a subset of the collection of edges from the original graph. So in this case, I will pick these two edges. So there's a subgraph of G. How about another subgraph of G? Maybe we'll say another subgraph. In this case, we'll use all of the original vertices. So 1, 2, 3, 4, 5. And the edges that we'll use will just be these edges here, 2 connecting to every other vertex. Now, in both of these cases, the graphs I've drawn are subgraphs of the original G. But to illustrate what that last part of the definition in terms of spanning actually means, if I look at that first example of a subgraph consisting of the vertices 2, 3, and 4, this is not, put this in parentheses here, not a spanning subgraph. Why is it not a spanning subgraph? Well, in order to be a spanning subgraph, the vertex set of the subgraph has to be equal to the vertex set of the graph. In this case, I'm missing vertices. In my subgraph, I don't have vertices 1 and 5. So it's not a spanning subgraph. The second one, however, is a spanning subgraph. So this is a spanning subgraph. Why is that? Because it has all of the original vertices. So not only is it a spanning subgraph, it is also a tree. It doesn't have any cycles in it, and it's connected. So this is a graph, which is a subgraph of the original, uses all the vertices, so it's a spanning subgraph. It's also a tree. So we refer to this as a spanning tree of G. Those are things we'll investigate a little bit more thoroughly later on in the course, but this is something you may have heard before. You may have heard of the term spanning tree. A number of algorithms in graph theory depend on this idea of finding a spanning tree. A lot of searching algorithms depend on spanning trees, and so that's just a quick illustration of what a spanning tree is. So now we can count some more things. How many spanning subgraphs does the complete bipartite Kn1, N2 have? Well, again, it might be helpful to think in terms of a picture. So we've got our vertex set V1, which has N1 elements, our vertex set V2, which has N2 elements, are edges that connect. There's lots of them. Even more in the dot, dot, dot. So there are n1, n2 edges. And this is our graph kn1, n2. How many spanning subgraphs does it have? Well, spanning subgraph has to use all of the original vertices. And so there's really a question about which edges can we choose. So our choice is really about edges. So how many spanning subgraphs does it have? It's really about how many possible ways are there to choose edges to fill out your graph. There are n1 times n2 edges. Each one of them can either be used or not. So the number of spanning subgraphs is equal to 2 to the n1, n2. Now you'll notice that this is pretty much the exact same question as how many graphs have a bipartition v1, v2. It's actually the same question. It's just now I didn't have to introduce sets v1, v2, their sizes n1, n2, and then phrase the question as how many graphs have this bipartition. Instead, we phrased it in terms of subgraphs. So how many spanning subgraphs does the complete graph have? It's the same solution process, just a different way to phrase the question. How about 10? How many spanning subgraphs have exactly m edges? So in this case, we have the number of spanning subgraphs with m edges. Well, again, we have a collection of n1 times n2 edges, and we want to select m of those in our spanning subgraph. So from n1, n2, we're going to select m. Let's go ahead and introduce a couple more structures, paths and cycles. We've already looked at these as graphs themselves, a path graph, a cycle graph. Now we're going to look at paths and cycles living inside larger graphs. So if P is a subgraph of a graph G, and it is also a path, we call it a path of G. If C is a subgraph of G, which is also a cycle, we call it a cycle of G. So for example, we could have the vertex starting at 1, we could use the edge connecting it to 2, and then the edge connecting it to 3, and then the edge connecting it to 4, and then that edge connecting it to 9. So 1 to 2 to 3 to 4 to 9 is a path in G, or a path of G. How about a cycle? Well, we need to identify a subgraph which is also a cycle. Maybe I'll take 1, 2, 7, 10, 5, and 1, and those edges that I've identified. So 1 to 2 to 7 to 10 to 5 to 1. That is a cycle of G. In each of these cases, we can also identify the length. What is the length of the path? Well, the length of a path, or the length of a cycle, is the number of edges in it. So this has 1, 2, 3, 4. So this is of length 4. Whereas in this case with the cycle, this had length, or has length 5. The next question is asking us how many 4 vertex paths does the graph Kn have? So if we're in the complete graph on n vertices, how many 4 vertex paths does it have? So the way I'm going to think about this is I'm going to write out a generic path. So it would be vertex, edge, vertex, edge, vertex, edge, and then vertex. And now I can ask the question about how can I fill these vertices. So how many choices are there for that vertex? Well, there are n choices, because there's n vertices in Kn. So there's n choices to fill that slot. There are n minus 1 choices for this one. There are n minus 2 choices to fill that one, and so on down the line. This fourth vertex, I've already used up 3 of them. Of the remaining n minus 3, all of them do connect to the previous vertex, so there's n minus 3 choices for this one. Now, I have double counted, because if I, for example, chose vertex 1, then 2, then 3, then 4, I get the same path as choosing vertex 4, then 3, then 2, then 1. It's the same graph. 1, 2, 3, 4, 4, 3, 2, 1. Those are the same graphs. So I have to realize that I'm double counting here. So the number of paths is equal to n times n minus 1 times n minus 2 times n minus 3 divided by 2. And that's because the opposite direction is the same path. And so what we have here is that the number of paths is equal to, I can write this as, it is n factorial on the top, and then what I've lost is the n minus 4 and smaller terms, so I could divide by n minus 4 factorial, and then I've got that division by 2, so 1/2. So there's a little bit more compact way to write the number of paths. So looking back at the solution I've used here, what I've actually done is counted the number of permutations of size 4 there are from the collection of n vertices. But I had to realize that I wanted to consider a permutation written in one direction is the same as the permutation written in the reverse direction. So that's where that division by 2 comes in, because a path is really direction independent. All that matters is the collection of vertices and the collection of edges. That's what determines a path. It's a graph. And so if I wrote down the ordering of the vertices in one direction and then reverse the direction, it's really the same graph. However, could I do this in a different way without having to appeal to permutations? And the answer is, in general, for most, if not all these problems in this course, the answer is always yes, there's an alternate solution. So what is the number of paths in this case? Well, what we can do is we could choose the 4 vertices first. So from those n vertices, choose 4 of them that you're going to use in your path. So now I've got this collection of 4 vertices. Here we'll give an example. Okay, I've chosen my vertices. I've got vertex 1, 5, 17, and 23. There we go. Those are the vertices now I'm going to use to make my path. Okay, so how many paths can I make with these now? I chose my vertices. How can I make my path? So what I could do is I could pick 2 of them. Let's just say 23 and 5. And those will be the ends of my path. Now for those other 2 vertices, there's really 2 ways I could fill in those positions. I could put, the 1 here and the 17 here, or vice versa. So there's really only 2 choices left. So once I've picked the 2 ends, then there are 2 choices to fill in these remaining spots. So that's just a bit of our brainstorming here. Okay, once I pick 4 vertices, what I'll do is I will pick from those 4 vertices, I will pick from them the 2 that will form the ends of the path. So choose vertices, choose the ends of the path, and we saw from our little brainstorming session there that once I've chosen the ends of the path, there is really, well, I won't even write it as a choice, there are really just 2 ways you can fill in the middle vertices. You either fill them in, as in this case it was 117 or 17.1. And so there is our number of choices. So we will choose order of middle 2 vertices. And so there we go. there's an alternate solution for the number of paths. You may say, well, those answers look different. Are they really different, or are they the same? Well, they actually turn out to be the same in this case, because we can write it out. What does n choose 4? That's n factorial over 4 factorial, n minus 4 factorial, times 4 choose 2. That's 4 factorial, 2 factorial, 2 factorial, times 2. These 4 factorials cancel. I've got a 2 cancels with a 2 factorial, and so what we're left with is an n factorial on top, an n minus 4 factorial on the bottom, and then a 2 factorial on the bottom is just a half. So there we go. It's a half n factorial over n minus 4 factorial, which is the same answer that we got by thinking about it in terms of permutations. So we thought about it in terms of combinations and then imposing order after, or in terms of permutations, fixing an order first and then removing over counting. So a couple of alternate ways to solve the same problem. The last kind of substructure we can get on a graph is this notion of an induced subgraph. So I'm going to back it up and go back to the spanning subgraph for a second. Because what did the spanning subgraph definition tell us? Well, the idea was we had this graph G, and what a spanning subgraph was that the vertex set is forced on us. Vertex set is forced. In other words, we have no choice over it. We have to choose all the vertices. Edges can be chosen. So that's what we have a choice over. So a spanning subgraph is one that has to use all the vertices, but you're free to take whichever collection of edges from the original collection of edges on the parent graph. So vertex set is forced, edges can be chosen. What an induced subgraph is we are free to choose the vertices now. And then the edge sets are forced on us. So induced means we can choose the vertices, and then from that, the edges are forced. And so that's what's described here. So once we have V prime, which is a subset of the original vertex set, the subgraph of G induced by V prime is the graph consisting of the vertices V prime and edges, which consist of all the edges from the original graph that connected to vertices in V prime. So let's have a look at an example. For this graph below, we're going to determine the induced subgraph for these vertex sets. So the vertex set given for A is 1, 3, and 4. So we're going to use 1, we're going to use 3, and we're going to use 4. And now we are forced to use whatever edges there were in the original graph that connected these vertices. And so if I look up, in the original graph I see that 1 didn't connect to 3 or 4, but 4 connected to 3. So there we go. There's our induced subgraph given by those vertices. Let's do another example. 1, 0, 3, 4 is going to be our next one. So 1, 0, 3, and 4. And so again, with an induced subgraph, the idea is you pick whatever vertices you want. In this case, we're told to take 1, 0, 3, 4. Once you have those vertices, you are forced to take the edges that exist in the original graph that connect any of these two vertices together. So we are forced to take 1, 0, 0, 4, 0, 3, and 4, 3. And so there is our induced subgraph given by the vertex set 1, 0, 3, 4. Right. There's an exercise at the end here for you to think about and ponder. It says if G is a graph with n vertices, how many induced subgraphs does G have? And so I want to just draw your attention. Induced. This is the key word, because what that tells us is that we are free to choose vertices, and then once we choose our vertices, the edges are forced upon us. So that can narrow in your thinking. How many induced subgraphs are there? Well, what do I have freedom to choose? I only have freedom to choose the vertices, because once vertices are chosen, the edges are forced upon me. So that may help in thinking about how many possible subgraphs there are. All right, that's it for this section. Thanks for watching, and we'll see you again next time.